Minton. These are some of my favorite math stories. In this episode, Mathematics is Symmetric. We'll look at symmetry, one of those things that we think we know what it means, but can be very difficult to define. Humans find that symmetric faces are more attractive than non-symmetric ones. But how would you measure that? Mathematicians have a definition for symmetry that mostly captures what we mean in everyday language while adding a dimension to the concept. A symmetry of an object is an action or transformation that leaves the properties of the object unchanged. First, notice that we are not evaluating whether an object is symmetric or not. We are identifying the symmetries that an object has, though an object with a common symmetry is likely to be thought of as symmetric. Take this equilateral triangle. All sides are the same length, and all angles are the same. If I reflect it across a vertical line as shown, swapping the left and the right, the triangle looks the same. This vertical reflection is the symmetry of the triangle. Now look at this arrow. It points to the right. Does it have any symmetries? A rotation of 360 degrees should work, of course. But how about a rotation of 180 degrees? Surprise! We'll come back to this unusual symmetry at the end of the episode. Back to the equilateral triangle. We have seen that a vertical reflection is a symmetry. So are reflections about the other two lines through vertices shown, lower left to upper right, and so on. Also, if we rotate it 120 degrees, it looks the same. A 120 degree rotation is a symmetry of the triangle. Similarly, a 240 degree rotation is a symmetry. If we add the identity, don't do anything, to the three reflection symmetries and the two rotation symmetries, we have the 6 symmetries of this triangle. If you're thinking like a mathematician, you would question why other symmetries don't count. For example, a 360 degree rotation leaves the triangle exactly the same. Why isn't this another symmetry? We need to be more precise about what our triangle looks like by labeling the vertices with A, B, and C as shown. Starting at the top and going clockwise, this is A, B, C. If we rotate this 120 degrees clockwise, we get the triangle shown. The triangle is the same, but the labels have a different orientation, now read as CAB. If you rotate the original ABC by 360 degrees, you end up with ABC. This is the same as doing nothing. So the 360 degree rotation is the same as the identity symmetry. What about a 240 degree rotation counterclockwise? It's certainly a symmetry, but it's the same CAB as for the 120 degree clockwise rotation. The 6 symmetries place the vertices at ABC, the identity or the 360 rotation, CAB, 120 degree clockwise rotation, or 240 degree counterclockwise rotation, BCA, 240 degree clockwise rotation, ACB, vertical reflection, CBA, reflection about the line through B, and BAC, reflection about the line through C. Can you see why we know that there are no more symmetries? Well, there are no other ways to order A, B, and C. In other words, for the triangle, we can simply list the order of the vertices instead of thinking of a geometric motion. An important step in learning to analyze symmetries is to learn how to multiply them. To multiply 120 degree clockwise rotations, do a 120 degree rotation twice. You should end up with vertices at BCA, the same as the 240 degree clockwise rotation. In other words, 120 degree rotation times 120 degree rotation equals a 240 degree rotation. Maybe plus would be a better word. What do you get when you multiply 120 degree rotation by a vertical reflection? The 120 degree rotation gets you to CAB, and if you then do the vertical reflection, you swap the A and the B to get CBA. That is, 120 degree rotation times vertical reflection equals reflection about the line through B. The study of the properties of these symmetries is called group theory, which can be learned in a mathematics course called abstract algebra. I think this is pretty cool, although I recognize that not everybody agrees with me. Is it useful? Well, the study of symmetries is used to classify one-dimensional and two-dimensional patterns, called strip patterns and wallpaper patterns respectively. The strip patterns, of which there are 7, use crystallographer's notation to classify the symmetries. These and the 17 wallpaper symmetries are used to classify types of pottery. Cultures tend to specialize in specific patterns, and classify crystals, among many other uses. Group theory is fundamental to much of modern physics. Symmetry magazine is an online journal about particle physics. I promise to return to the surprising arrow that refuses to turn the other way. How does this optical illusion work? Well, by symmetry, of course. On an overhead view, you can see the object actually has a symmetry of a 180-degree rotation. When it's tilted, you see the backside stick up higher, and our brain formulates an arrow. Rotated 180 degrees, we can see the same set of clues that there should be an arrow there. Pretty clever. There are many more ambiguous figures that are fun to play with, especially when a mirror shows a different image. Kokichi Sugihara has created many clever examples. I encourage you to look online and find some of those examples.